Howdy. I wanted to do a couple of examples of the trapezoidal error formula. I'm not going to present a proof of that formula, which is really beyond the scope of our course, but I do want to make sure that everybody is able to use that formula to answer a couple of basic questions. You remember that when we talked about the trapezoidal error bound, what we said was that this error bound is, as your book presents it, b minus a over 12 times h squared times the maximum value of f double prime, and it's the max on the interval a to b. Usually this part is omitted in the notation, but it's understood that we're looking for the maximum possible value just on the interval a to b. Now the h that it appears in this formula we've been using as delta x. And assuming equal spacing, that h is going to, or delta x is going to be b minus a over n. It's going to be the width of one trapezoid that we're using. If your trapezoids are not equally spaced, then you would use the width of the largest one. Because the delta x, or the h, is equal to b minus a over n, we can substitute in here and get a different expression for the trapezoidal error, which is b minus a cubed over 12 n squared times the max of f double prime, just like so. And that happens, again, just by substituting for h right there. We're going to find that this formula is going to be more useful to us for computational purposes. So what does it mean that this is an error bound? What this means is that the error bound is the worst case scenario. In other words, it doesn't tell me how much error I have exactly, but it says that my error is no worse than this expression right here. In other words, it is a bound on the error. In other words, if I find that this error bound is less than, say, 0.1, and my area is, let's say, 5, the trapezoidal estimate is 5, then that would mean that the true value of my trapezoidal estimate is somewhere between 5 minus 0.1 and 5 plus 0.1. The trapezoidal estimate itself is 5, but the true value of the integral, I should say, is going to be trapped between estimate minus error bound and estimate plus error bound. So that's the meaning of this. Now, how does this actually work out in practice? So let's say that I want to estimate the integral from 0 to 2 of x squared dx. Now, I'm just using this as a kind of example because we already know how to get the exact value using the fundamental theorem. And we'll do that at the end to find the true error in our estimate. Now, let's say we estimate with two trapezoids. And that estimate would then look like this. We would say that the trapezoidal estimate is equal to b minus a over 2n times f of x0 plus 2 times f of x1 plus f of x2. Draw yourself a picture to see what we're talking about. We're looking at two trapezoids here. And so there it is. By the way, since our curve is concave up, we can see that our trapezoidal estimate is going to be an overestimate. We expect that the estimate that we get is larger than the true value of the integral. Plugging in numbers, we get 2 minus 0 over 2 times 2 trapezoids times. Then our x0 is 0, our x1 is 1, and our x2 is 2. So that I get 1/2 times 0 squared plus 2 times 1 squared plus 2 squared, and the trapezoidal estimate turns out to be 2 plus 4 is 6 over 2 is equal to 3. Now, if I am so lucky as to know the exact value of this integral, I could tell you the actual error. And let's do that at this time, since this happens to be an easy function to integrate. Using the fundamental theorem, I get the integral of x squared from 0 to 2 is x cubed over 3, evaluated from 0 to 2, which is 8/3 minus 0, or is equal to 2.6667. So you can see that, indeed, my trapezoidal estimate is a little bit too large, and the actual error is the difference between the trapezoidal estimate and the true value, which is 0.3333 to 4 places. So that's the actual error. But let's suppose that we didn't know the fundamental theorem and we wanted to put a bound on the error. Suppose this computation is not possible because we don't know how to integrate. Well, in that case, we would say that the error bound is going to be less than or equal to, and here I'm going to use the alternate form that we talked about, b minus a cubed over 12n squared times the maximum possible value of f double prime. So we need some different components here. First, we need our b and our a, which are still 2 and 0. We need n, which is the number of trapezoids, like so. And we also need the maximum possible value of f double prime. Well, let's compute f double prime. If f of x, our integrand, is x squared, then f prime is 2x, and f double prime is 2, which is conveniently a constant, which means that its maximum value is 2. Now when we plug all this in, this gives us 8 times 2 over 12 times 4 is 48, so that I get 16 over 48, or 1/3. So that my error is no worse than 1/3, which interestingly just happens to be the actual value of the error that we got there. It wasn't entirely a coincidence. It turns out that the trapezoidal approximation will give an exact error for quadratic functions. So for other functions, we won't be so lucky. But for this particular function, our error bound turned out to be the actual value of the error itself. So, what would happen if I used 10 trapezoids instead of 2? I expect that the amount of error should go down. And I can find that amount of error without actually going through and computing. And that would give me an idea of whether or not it's worth computing the actual sum with 10 trapezoids, which we agree would be kind of a pain in the neck. We could do it. It would just take us about 10 or 15 minutes to write it all out, and so on and so forth. So let's find the error bound and see if it's worth doing. Again, the error bound is less than or equal to b minus a cubed over 12n squared times the max of f double prime. And we get to recycle a lot of our work because the b and the a are still 2 and 0. But now the n has changed. I'm using 10 trapezoids instead of 2. And the max of f double prime is still 2. So this now gives me 16 over 12 times 100, or 4 over 3 times 100, or 1 over 75, which is a little bit greater than 0.01. So I can see that by going from n equals 2 to n equals 10, I would improve the accuracy significantly. My error would go from 0.33 to no worse than 0.01. Well, let's take a look at one more example. we want to sort of reverse engineer the question here. Suppose we have the integral from 0 to pi of sine x dx. And I want to ask this question now. How many trapezoids should we use so that the error is no greater than 0.001? In other words, what I would like to do, this is actually a practical question for a computer. What I would like to do is I would like to compute this integral so that my answer is good to plus or minus 0.001. And now the question is, how many trapezoids should I use? So we're going to, again, use the error-bound formula. Error-bound is trapped between, or is bounded by, b minus a cubed over 12n squared times the maximum possible value of f double prime. Okay? So in this case, our b and our a are pi and 0. And the n is unknown, so I'm going to leave that as n, just like that. What about the maximum value of f double prime? Well, my integrand, f of x, is equal to sine x. So f prime is equal to cosine x. And f double prime is equal to negative sine x. What is the maximum value of the absolute value of this second derivative? Well, I know something about negative sine x. I know that from 0 to pi it stretches from 0 all the way down to negative 1. So that if I take the absolute value, here's the absolute value of negative sine x, then my maximum possible value is 1. And what I want is for this error to be no greater than 0.001. Well, now, this gives me an inequality that I can solve pretty easily for n, simply by clearing the fractions. What I get is pi cubed is less than or equal to 0.001 times 12n squared. In other words, n squared is greater than or equal to pi cubed over 0.001 times 12. Now, I don't know what that number is, but we can compute it pretty quickly as 3.141596 to the third power divided by 0.001 divided by 12 is 2583.9. Now that's huge, but we get to take the square root here. Nope, that didn't do an inverse formula. Why not? Oh, because there's my square root. 50.83. Now, what does this n value tell me? It tells me that if I use any number of trapezoids greater than 50.83, in other words, 51 or more, then my error will be no greater than 0.001 in magnitude. There are a couple of things that I want to observe in closing about our error-bound formula. And the first is that the wider my interval, the greater the error is going to be. And the second is that the larger the number of trapezoids I use, the smaller the error is going to be. And that drops off with the square of the number of trapezoids, so that the trapezoidal approximation improves very quickly as we increase the number of trapezoids. If I go from 1 to 10, my error drops by a factor of 100. If I go from 10 to 100, my error drops by another factor of 100, and so on. And the final thing I want to observe is that the error is proportional to this maximum value of f double prime. In other words, a function that has a lot of curvature to it, so that f double prime is large, is going to have a lot of error in its trapezoidal approximations, because the trapezoid is going to cut across a deep valley or a high mountain. But if f double prime is very small, in other words, my curve is not very curvy, but it is close to a line, then the trapezoidal approximation is going to be pretty good. And in particular, if my function happens to be linear, so that f double prime is exactly 0, then the trapezoidal approximation will actually be the exact value.